In this lesson, we're going to talk about probability plots. And these are very useful for exploring data and also for thinking about statistical concepts. First, let me introduce the QQ plot. When we begin to explore data, we may want to explore how closely one vector of data matches the distribution of another. So let's start with the easy QQ norm function, which compares any data vector to a normal distribution. So I'm going to create a random normal vector of 100 observations. And then I'm going to use the QQ norm function on that data set. After we execute the QQ norm plot, we can add a QQ line which adds a line to a normal quantile plot which passes through the first and third quartiles. The closer the data points match the line, the more closely the data vector follows a normal distribution. So let's add that line real quick. QQ line X. And when we zoom into this plot, we can see that it matches pretty closely. Of course, there are some fluctuations, but I'm pulling random numbers from a normal distribution, so we expect it to be somewhat close. Now let's load the Cars 93 dataset using our data function. I'm going to attach the dataset. Now when I attach the Cars 93 dataset, it's sharing a lot of variables with some data I had loaded in here from previous lessons. The following objects are now masked from these two different datasets, but you can ignore that. All it means is that it's going to no longer pull information from those two datasets when I call the variable names. So now let's try the QQ norm function on one of the Cars 93 variables. And then I'm going to throw in the QQ line, and we'll see how closely it matches a normal distribution. And we can see that it doesn't do too great. On the tails, it doesn't meet the line at all. A similar function is QQ plot. And for this function, we enter two different arguments to compare the distributions against each other. No longer concerned about normality, but how closely the two datasets match each other. By doing this, we can compare any two datasets to see if they share some underlying characteristics. Secondly, we can compare a data vector to different random datasets to see how closely they match that distribution. So I'm going to create a random dataset called Y. It's going to be 100 observations. We can use the QQ plot function to compare X and Y, which both come from a normal distribution. So we should expect them to line up and have similar distributions. For QQ line, use the second argument that you threw into QQ plot. So we're going to use Y. And we can see that there's a little more noise, and that's because one distribution matches somewhat closely to the normal distribution while the same for the other ones. They can be even further apart. Now let's compare our random vector X with miles per gallon in the city. And we can see that it looks very similar for when we used QQ norm on the miles per gallon. And we expect that because the X vector comes from the normal distribution. So now let's compare two of the variables from the Cars 93 dataset. We'll compare miles per gallon to engine size. So they look like they're probably similar distributions because of how they line up so well. Let's add in QQ line. So why is the QQ line all the way out here all of a sudden? Well, the data are actually on different scales or magnitudes. So we first need to scale the data using the scale function. The scale function centers the data around 0 and shrinks it so that the magnitudes of the datasets match each other. So let's run the QQ plot again, and for each argument, we'll wrap the variable of interest inside the scale function. And then for our QQ line, we'll do the same thing. We're going to scale our miles per gallon. Now the line is where it should be. We can see that these distributions match each other pretty well, except for at this extreme tail over here. So let's look at the scale function a little more closely. Create a vector of numbers, and I'm going to scale that vector. It's going to return each element scaled, and it's going to show you how it centered it and how it shrunk it. So if we calculate the mean of that same vector, we can see that the scaled center is the same. And if we use a standard deviation on X, we'll see that that's where it gets the scale from. If I subtract the mean from X and divide it by the standard deviation, we should get the same results as the scale function. And you can see that that's the case, although it returns them slightly differently. We can see that the first element is negative 1.4, same as with the scale function. Now, what if we wanted to compare the distribution of miles per gallon to a different distribution than the normal data set? Why don't we try the chi-squared distribution? So I'm going to set up a QQ plot, and I'm going to use the scale function, and I'm going to get some random numbers from the chi-squared distribution. And I want to make sure that I have as many observations as there are in the Cars 93 dataset. So I'm going to throw in the number of rows of Cars 93, and that's how many observations of my random chi-squared dataset I'll have. Next, I'm going to compare this to the scaled version of my miles per gallon. And lastly, for this R chi-squared distribution, I can't forget to set my degrees of freedom. So I'm going to set my degrees of freedom to be 5. We'll see how that looks to start off with. Lastly, I'm going to throw in my QQ line for the scaled version of the miles per gallon. We can see that the distribution of miles per gallon fits much more closely with the chi-squared distribution than it does with the normal distribution. There's still some error off on this tail, but it still looks better at the lower tail than it did before. In this data set, we talked a little more closely about how to explore probability plots and how to explore what distributions different variables might have. And this can be very important for when you're picking which models to run on your data.